So, earlier we discussed some basics of what a reproducing kernel Hilbert space is. Now, we will get into the details of the representer theorem, which means that any function in this reproducing kernel Hilbert space can be expressed as a linear combination of Mercer kernel functions. So, I state this theorem. Any function defined in a reproducing kernel Hilbert space can be represented as a linear combination of Mercer kernel functions. So, here is a sketch of the proof. So, we define a space which is the reproducing kernel Hilbert space induced by a Mercer kernel, and given any real valued function, we decompose this function into two parts, one function that lies in the span of this kernel and the other which is basically in the orthogonal complement. And then we look at the inner product of this function with the kernel, and then we simplify our details using the reproducing kernel property, okay, and that is the simple idea. So, let us delve into the details. Okay. So, the proof begins as follows. Define a space H that corresponds to the reproducing kernel Hilbert space. Define a space H to represent the reproducing kernel Hilbert space induced by a Mercer kernel, and I call this kernel to be K acting on some vector x, and this dot indicates its a data point xi. Okay. Now, the salient idea is given any real valued function f belonging to this space script H, which is representing the reproducing kernel Hilbert space, we could decompose f into two components lying within this space H, and one is an orthogonal component of and these are orthogonal components. Okay. So, what do we mean in terms of the precise language of math here? The first component, which is denoted by f, I call it parallel here, f parallel, is contained in the span of the kernel functions kx1 dot kx2 dot so on. So, I can write f parallel acting on some data vector is summation I equals 1 to L ai, the kernel acting on xi and that data vector x. Okay. Let me call this equation 1. The second component is orthogonal to the span of the kernel functions. So, what it means is take a linear combination of the kernel functions to form a function f parallel, and this function which is I call f perpendicular acting on this data point is orthogonal to the function which is obtained from the span of the kernel functions, right. The second component is orthogonal to the space of the kernel functions, and it is given by f perpendicular. Okay. So, this function f now can be expressed as f parallel plus f perpendicular, and one can think about visualizing these functions as residing in spaces that are orthogonal complements of each other. Okay. So, I call this equation 2. Let us use equation 1 in 2 and then simplify. So, f is basically summa I equals 1 to L ai kernel acting on xi dot, the dot indicates I can replace it by a vector x, plus f perpendicular acting on the vector x. Now, from the reproducing property of the Mercer kernels, f of xj can be written as the inner product of, I take the function on some data point and I take the inner product with the kernel acting on xj with this data vector, and that gives me back this function. So, I take the function, I take the inner product of the function with the kernel and I get back the function, right, where this inner product is over this Hilbert space. Now, what I do is I take f based on this expansion. So, I call this, I think I call this is equation 2 here. So, this should be equation 3. I plug in equation 3 into 4. So, what I get is f of xj, because it is any function on this data point. Now, I expand f in terms of two components, which is summation I equals 1 to L ai, because it is lying in the span of the kernel functions, this with kernel okay. Now this distributes. Yeah, in the slide I had this as f parallel, this has to be f perpendicular, right. So because we have a function that can be represented using the kernel functions, and then a function which is orthogonal to the kernel function, right, which lies in a space which is orthogonal to the kernel function. So this had to be a perpendicular consistent with equation 3 that I have here. Okay. So let us simplify from this. I simplify f of xj, which is the inner product I equals 1 to L AI kernel acting on xi dot. I think you have to pay attention to the way I have written it down here. So AI times kernel xi dot, and I get this kernel here k xj dot plus the inner product. I mean, I have to put this inner product here, right, inner product of this function with this function. So there is a comma here, inner product of summation AI. Basically this is a function which is in the span of the kernel functions. I take the inner product of that function with the kernel. This is my first term, and my second term is inner product of the, this is the orthogonal component, this is f perpendicular with kernel xj, kernel acting on xj and dot. Because this orthogonal component is, because this orthogonal component f perpendicular is orthogonal to the kernel function. So this evaluates to 0, and all we have is the inner product of the kernel with this function which is a parallel component, which is basically a linear combination of these kernel points. Right, I take the inner product, the second term is 0, the first term is basically an inner product of the kernel xj with data point x with the kernel xi and another data point x. Right, by our definition we can write this is summation I equals 1 to L AI times kernel xi, kernel acting on xi and xj, right. So this is because k of xi comma xj is xi dot kernel, the inner product of xi with the data vector and xj with another data vector. That's our definition of the kernel in this form. So now what this means is I can express any function in a reproducing kernel Hilbert space as a linear combination of Mercer kernel functions. So these are Mercer kernel functions, and we have a linear combination of Mercer kernel functions, and that is how I can represent any function in the reproducing kernel space, right. I think what we have done is pretty straightforward. So, just to sort of summarize, this is a very important result. So, what I have done is I define a space to represent the reproducing kernel Hilbert space induced by a Mercer kernel, and I take a real valued function belonging to this reproducing kernel Hilbert space and decompose this into two components. One lies in the span of the kernel functions and the other lies in the space which is orthogonal to the kernel functions given by f perpendicular. So, f can be written as f parallel plus f perpendicular. Now, what I do is I invoke the reproducing property, right. So, f acting on some data point can be obtained as f acting on some other data point with the kernel between a different data point and this point xj, right, and that is the reproducing property of the kernel. So, this is very important. So, what I do is I plug in f, which is basically having two components, one in the span of the kernels and the other is in the other is in the orthogonal space, is in the orthogonal complement of that space, right. And I take the distributive property, expand the inner products carefully. The inner product of the function f perpendicular with the kernel is 0 because it is how we have decomposed our space by our construction. So, all we land up with is the function which is a linear combination of these Mercer kernel functions. So, this is a very important and an interesting result which has interesting applications. And when we talk about the general applicability of this theorem, particularly when we have to minimize the empirical risks of functions. I mean, when we think about empirical risk that we want to minimize along with some regulatory conditions over functions in the Hilbert space. So, I am given some data samples, essentially I give you some data samples xi and di, and I want to minimize the risk. Maybe it is a risk in the classification error or anything that I want to think about, and within that framework I want to bring in these ideas of kernels, maybe in the SVM framework or an extended SVM framework along with regulatory conditions, then this result is going to be very useful for us. Okay. So, with this we will stop and we will discuss the general applicability of the representer theorem.